Hello, 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 ladies and gentlemen. Welcome. Today I'm going to be going through the history section for Unit 1. So there is a worksheet to go along with this. It is this here. Okay, this is kind of a summary page of the notes to try and help you organize the information. If you were stuck at home, then you can't get the hard copy. I'm going to show you where to find this in Canvas first, and then we will start on the notes. So if you go into Modules, and then Topic 1.3, and it is Worksheet 1.3a. So this is the worksheet. You can print this out, or you can come up and make a copy of it. Hang on, I've got the screen on. You can come up here, hit make a copy, and save that in your physical science folder. And that way you'll have a copy of it that you can edit online, and then you don't have to write everything. So yeah, I'm going to go through this. I'm going to pull the notes up, and I'm going to mention the things that need to go in here. I do want to point out the headings on here because I've had people get a little confused. The different folks that we're going to be going through, they're going to be listed on this side. For some of them, we're going to be talking about their experiment. So what the experiment was called, and a picture of what it was, what their contribution was to our modern understanding of the atom, and then the model they came up with. We're going to talk about several different models of the atom. Okay, so the name can go in this column, and then again, there'll be some kind of image to go here for most of them. Now, a lot of these, you'll already notice, have X's in them. That means you don't have to put anything in that cell. That's either something we're not going to talk about or something that you don't need to worry about. So yeah, I'm going to pull up the notes, and then we'll get started. Okay, I have also moved the camera a little closer, so hopefully that will make it a little easier to see what is going on. All right, the first two guys we're going to talk about are Aristotle and Democritus. Now, these two have a distinct difference from everyone else we're going to talk about, because these two are not scientists. You can kind of tell by the dates here, BC, and again, BC. These two were Greek philosophers. Okay, these two contributed a lot of ideas at the time. In fact, Aristotle was one of the first to really try to classify matter. So we are going to talk about these guys. We're not going to say too much about them other than, hey, these guys existed too. Yeah, these guys aren't really scientists. So there's no experiment for these two because they didn't do any experiments. Aristotle was the first person, as I said earlier, to try and classify matter. Okay, he took the world around him and he tried to break it up into elements. Everything has to be composed of one of these elements. And he came up with four. Four that I'm sure some of you are going to recognize. Earth, fire, air, and water. Which obviously are pretty prevalent today in society as magic systems in different fantasy worlds. There are others beyond these, but Last Airbender, Pokemon, and a myriad others all use this core system for their magic systems. Which wasn't what he had in mind. He genuinely thought he was organizing matter, but a lot of what he said we now know was wrong. But he's still the first person to try, or at least the first recorded person to try. And I personally think that still bears mentioning. Now, the way he divided these four elements up was based on four properties: hot, dry, cold, and wet. So yeah, I'm going to put a little diamond thing up here. Yeah, I will point out this you should have in parentheses, the date here. It might be easier to put this under instead of in because it is a date range rather than a specific date. And I'm going to draw a picture up here. I'm going to probably pause this so the video doesn't get too long. Draw this picture up here and then unpause it so you can see that. So I'll be right back. All right, so this is the sketch that you want to put in your model for Aristotle. Okay, he took the 4 elements and he said each one of these elements is opposed to another one of these elements. So obviously, fire and water are opposed to each other, and air and earth are opposed to each other. And I will mention that while fire is almost always at the top, air and earth can be flipped as long as the properties are flipped too. It's not going to make a huge difference on this. So, yeah. He said every 2 elements share one property, or every element shares one property with another element. So fire and earth are both dry, fire and air are both hot, air and water are both wet, and water and earth are both cold. Now, obviously, like as some of you pointed out, some of my students pointed out in class, air can be hot or cold, and air can be wet or dry. It varies quite a bit. So, as we said earlier, the system doesn't work 100%. It was a really good idea at the time, considering the evidence that they didn't really have. They knew rain came from the sky, therefore air must be wet. You know, earth tends to be dry unless you add water to it. It made sense with the information they had. And that's pretty much it for Aristotle. I will tell you, you have to make sure you have the properties and the elements straight in your head. Because if I ask you what were the 4 elements that Aristotle broke everything up into, these are the answers. But if I say what are the 4 properties he used, these are the answers. So properties, elements. Keep those straight because those are that's a 4-point question that you can easily get wrong if you put the wrong one in there. And with that, we shall move on to Democritus. Now, Democritus obviously lived before him, but, oh well, Democritus proposed a thought experiment. And his idea was if we, it is sometimes called the cut it in half experiment. Let's say you have a block of wood, okay, and you cut that block of wood in half. You now have 2 smaller blocks of wood. Well, if you take one of those and you cut that in half, and then you take one of those and cut that in half, and you cut that in half, and you cut that in half, and you cut that in half, he said at some point, if I cut it in half, it will no longer be wood. If I cut it in half, I will fundamentally change the structure of this thing to where it is no longer the same thing that it was before. Okay, and he called that smallest unit, this smallest point where you can't cut it in half anymore, he called it atomos, okay, which was Greek for indivisible. Okay, I would highlight that. Now, what he called an atomos, or an atom, because he coined the term atom, that's his contribution. What he called an atom, we now know to be a molecule. So again, not 100% accurate, but you're going to see that a lot as we move through this. Not 100% accurate, but it was pretty impressive that he came up with this with no scientific evidence at all. So yeah, from there we're going to go on to our scientists. You should have Aristotle's model image, Democritus's contribution, and then Aristotle and Democritus's dates for both of those. Now I'm going to clear the board and scroll down, so I'll be right back. All right, now we have Dalton. Okay, so Dalton published his scientific advancement in 1903, and for all, that's in 1803. And for all of these scientists, you're going to see a single date rather than a date range. That's because we know when they made their information public. We know when they published their research. For the guys who lived 2,500 years ago, we're less sure about exactly what they said happened, when they published, when they said, hey, this is what we think is going on. So it's a date range for them. But for these guys, there's a specific date. Now, the first thing that you need to do for Dalton, and this is going to be a little tedious for some of you, but do your best, you need to copy down his 5 rules. I'm going to step off to the side here so that you can pause this to copy those down. Okay? Going once, going twice. All right. I'm now going to assume that you have those written down. So he wrote 5 rules. He said that all matter is composed of extremely small particles, which he called atoms, which is true. Atoms cannot be subdivided, created, or destroyed, only change from one form to another. In all chemical reactions, atoms can be combined or separated. Atoms of a given element have the same properties. Atoms of different elements have different properties. And atoms of different elements combine in simple, whole number ratios to form chemical compounds. Most of what he came up with was true. We are not going to get into his experiment because it's a little complicated for this level. He had a solid understanding of what he was doing, though. One of these rules was wrong, and part of my goal is that by the end of this video, you figure out which one it is. Now, I don't care if you know the number or not. I want you to know which part of the rule. So I expect you to be able to tell me what rule was wrong. Don't say, Rule 3 was wrong, or Rule 1 was wrong. Tell me what was wrong about it. Okay? So keep that in mind as we're moving forward. We're not going to do anything with his experiment. His contribution is these 5 laws, one of which is wrong. Okay? Now, his model was called the billiard ball model, which I need to write down probably. I'll write it in red so it's a little easier to see. Okay, he believed in or ascribed to the billiard ball model, which is what pretty much everyone thought was correct at the time. Okay, billiard. Now, billiard, some of you may more commonly know as pool. It's pool table with the balls that you hit into each other with a stick. Okay, that's what billiards is. Okay, the billiard ball model was the idea that the atom was just a sphere. A solid sphere that could not be subdivided any farther. So that's his model name, that's his model diagram. And with that, we have finished the first half, theoretically, of the notes. Now, I'm going to go ahead on in this video and do the second half as well. Hopefully this won't be quite so long as the first half. But yeah, we're going to go ahead and run through these. So now, next we have at the top of the second page, J.J. Thomson, 1904. This time it is 19. Okay, now Thomson is the first person whose experiment we are going to talk about. Now, the experiment he did is called the cathode tube experiment. Okay, I'll just put that here. A cathode tube. Now, cathode tube is basically just a glass bulb with gas in it. Okay, so he had a glass tube, and he had wires running off of the ends. And what he did was when you hooked this up to a power source, a line of light would run from one end of the tube to the other. Okay? And he was doing something else. By the way, this is a common theme in science. Most of our really important discoveries were made by accident. Penicillin, discovered by accident. The electron, discovered by accident. Thomson did not keep his workspace very clean. He had a magnet sitting out just on the table next to where he was working, which is something you're never really supposed to do. You want to keep the number of variables in your experiment to a minimum. But in this case, it worked out really well because Thomson noticed that the beam of light, which is supposed to go straight across this tube, I'm not good at drawing these, but this is supposed to be like a uniform tube, okay, that the light went, instead of going straight across from one wire to the other, it bent. It was deflected slightly. And as he moved the magnet towards and away, the deflection of the beam changed as well. Now, based on what he knew about electricity, he concluded that the model of the atom, this model here, could not be correct, because if it was, the beam would not be deflecting. And so he proposed what was called the plum pudding model. By the way, that's the diagram for Thomson. That's it, okay, for his experiment. The plum pudding model, which I have here, okay, the plum pudding model is, he chose plum pudding because it was a really common dessert at the time, less common today, obviously. So instead of plum pudding, think of it like a McFlurry or a Blizzard. Okay, he said that for him, most of the atom is the pudding. Okay. Okay, and that pudding, or that atom, is composed mostly of just free-form matter. Okay, and it's positively charged. But embedded within that are these little tiny things, which we now call electrons. He called them something else, but we now call them electrons, that were negative. And he said, these are the plums. Now, if you want to imagine this as, like I said, more like an ice cream flavor, like a McFlurry or something, then the positively charged matter would be the ice cream. And the negatively charged particles, the electrons, would be whatever topping you put in your McFlurry. Oreos, M&Ms, Heath bars, whatever. Okay, the candy that is added to it. And this became the prevailing model for a little while. So this is the image of Thomson's model. This is the image of Thomson's experiment. And then this is the name of the experiment. There should be a space between this E and this T. Cathode tube. 2 words. All right. Now I'm going to clear this. So you've got a couple seconds to pause it before I move on. And time is up. All right. Rutherford. We fast forward another couple of years to Ernest Rutherford, 1911. He did what was called the gold foil experiment, or at least he gets the credit for it. Okay, something you need to know, pretty common back in the day. Scientists were busy doing their own thing, and so they would take their grad students, their assistants, and say, hey, go do this. And so actually his assistants did this experiment, not him, but he gets the credit because he's the one who got, his name was on the published paper. So yeah, his assistants, his grad students actually did this experiment. But the gold foil experiment, what they did was they took a piece of gold foil, which I'm going to use green for, because if I use yellow, you're not going to be able to see it. Okay, and gold foil or gold leaf, it's a very, very thin sheet of gold that you can use to make not gold jewelry look like gold. They put it on wooden picture frames, really common back in the day. But it's very, 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 very thin. Far, far thinner than a gum wrapper. Okay. So they mounted this, and then they put a sheet of phosphorescent material around most of it, and put that some known distance away from a radioactive source. Now, this radioactive source was basically a lead box with some nuclear material inside of it. And that nuclear material would occasionally send out a nuclear particle, or radiation, form of radiation called an alpha particle. And what would happen, and what was kind of expected to happen, was those radioactive particles would come forward, and according to Thomson's plum pudding model, they were far more massive or heavier than anything in the atom that they could encounter. And so they would pass through the gold foil, possibly being deflected a little bit, and then they would hit this film. And when they hit the film, it would light up for a second or two. It would glow, and then it would fade. And so they expect to see some small deflections, a lot of lights around the side. What they did not expect, which kind of was like, hold up, wait a minute, something's wrong, they got some massive deflections off of this. There were some particles that came to the foil, and then they lit up over here, or over here, or over here. And Chadwick, the assistant, and I don't remember who the other one was, but Chadwick was one of the assistants, and he's like, that's not possible. This cannot be happening. And he came up with the idea for the nuclear model. He said the only way this is possible is if if all that positive matter, instead of being spread throughout the atom, is concentrated in the center at the nucleus. Okay, and that's what he called it, was a nucleus. And so he proposed the nuclear model of the atom, because he added the nucleus, that there is a positive chunk in the middle, and then around that in the atom, there are negative electrons floating around. But this center piece is positive. He said the only way this can happen is if those positive radioactive particles are coming really close to this nucleus, and getting deflected by it. Okay? And so he proposed that nuclear model. Now, the details on why they came to this conclusion, you don't necessarily need to know. But this was the gold foil experiment. This is the nuclear model of the atom. Okay? And Rutherford published it, so he got the credit. Rutherford did point out that there are some potential issues with this, chief among them being positives and negatives are attracted to each other. Like, if this is what it looks like, these would all just fall into the center of the atom. There's no way that these charges are just floating around. And so he's like, why don't they just fall in? Why don't the negative electrons just go to the nucleus and boom, no more atom? Why do they float? That doesn't make sense. And Chadwick went on to prove the existence of the proton, but we don't have him in this, but you might be worth jotting down. Chadwick discovered the proton a couple of years later. But that's all I'm going to say about that. Next we have Niels Bohr, okay, who had a rough life, but he proposed the planetary model or the orbital model. Either of these names will work. Planetary model, I think, is how most people can remember it, but orbital is what it's officially called. I will go back and forth between these, so I would know both of them. Okay, the orbital model was the idea that the electrons, the reason they don't fall into the nucleus was because they are orbiting it, like planets around the sun. Okay, the law of gravity says that the moon should fall to the earth. Like, it should just hit the earth, boom, we're all dead, the end. Why isn't it? Well, because it's moving sideways fast enough that as it falls, it just keeps missing. Okay? And so Bohr proposed the same idea for these electrons. Rather than just floating around, they have fixed paths that they orbit the nucleus in, much like planets going around the sun. And so he said that the nucleus is a positive center, or the nucleus is the positive center, and then the electrons are going around it in an orbit that have fixed intervals. And that solves the problem, because if they are moving laterally fast enough, then they can't fall into the nucleus. Now, this had its own problems, because this means that electrons are moving really, really fast. And we'll talk more about that in a later unit. But in order for this model to work, the electrons have to be booking it. Okay? Far, far faster than the planets are traveling around the sun, because the electric force between these particles is far, far stronger than the gravitational force between the planets and the sun. Okay, so he proposed this, and that solved Rutherford's problem of why don't they fall. Now, there is no experiment for Bohr. He is what we call a theoretical physicist, or he was. He's dead now. He was a theoretical physicist, much like the next guy we're going to talk about. They didn't get out and do experiments so much. The argument could probably be made that Rutherford was a theoretical physicist as well, because he didn't do the experiments. He had somebody else do the experiments, and then he took the credit for what they discovered. But Bohr is the one who came up with the orbital model. It does have its own problems. It works 100% of the time for hydrogen. It doesn't work for any other element. To solve other elements, we would need a guy named Schrodinger, which is the last guy on our list. So I'm going to clear this, scroll down to Schrodinger. I am not going to have you draw a model for Schrodinger, but I am going to link a video for you to check out because this is pretty cool. All right, Schrodinger, about, I don't even remember what the last date was, but 13-ish years later, Schrodinger was another theoretical physicist. You probably know this guy as the cat guy. Schrodinger's cat. The cat is both alive and dead at the same time. That guy. Okay. He proposed what we call the, where is it? Hang on a second. All right. You need to write down the quantum model, because apparently I didn't get that into the notes. Schrodinger proposed the quantum model. Okay, now his model was based again in theory. There is not really any evidence for this other than the fact that Schrodinger's equations work, whereas Bohr's equations don't. Which is pretty hard proof when it comes to stuff that you can't see. So Schrodinger said that there are not fixed paths for the atom, but rather they are statistically more likely to show up in different places. And we're not going to go too in-depth on this, other than he proposed the existence of subshells, which those of you who go on to chemistry, you'll learn about SPD and F subshells, which are the different statistical regions where those electrons can or could be found. His explanation explains why electrons are able to move around more readily, because Bohr's model doesn't really allow for that very well. It's possible, and I'm going to say we are going to use Bohr's model of the atom in this class. We're not going to use Schrodinger's, because while Schrodinger's model is much more accurate, it is difficult to talk about or draw or visualize in any way. And I've got a video linked here. So if you've got the notes pulled up in Canvas, you can click on this. Also, this video is going to be linked on topic 1.3, which is where you got the link to this worksheet. Okay, it is also going to be linked on that page, so you can go and watch this video. But this, I'm not going to play it here because I'm pretty sure that would be plagiarism. I'm not going to show this video here, but it gives you visuals of what Schrodinger's atoms actually look like, which is really, really cool. Now, that's pretty much it for this. There is a worksheet. It's a practice quiz that has questions about all of these guys, what their discoveries were, what their models were. I'm going to tell you there are questions in there about the years. I am not going to test you over the years. Okay, I'm not going to ask you, what year did Schrodinger propose his quantum model? What year did Rutherford take credit for the nuclear model? I'm not going to ask you that stuff on the test, okay, or on the quiz. There's not stuff that you need to really know for the test or the quiz. Those questions are on the worksheet. But I'm not going to test you over those. I've had people end up spending way more time trying to memorize the dates than memorize the models. The models are the more important thing. The contributions are the more important thing. Which, by the way, his contribution here was the... oh, I didn't say, hey, let's go back to Rutherford. Bohr's contribution was the subshells, or energy levels, and Schrodinger's contribution was the subshells. So I apologize for skipping those. That's why it's a good idea to teach this before I actually try to make the video. So yeah, that's pretty much it here. Go through, take a look at that worksheet. This quiz is scheduled for whatever date, and I will see y'all next time.